Edexcel Core Pure, Hyperbolic Functions 1 and Introduction. Definitions and graphs of hyperbolic functions. In the next few videos we're going to be working with some new functions called hyperbolic functions. An example of this is if you take a heavy chain which is hanging under its own weight, it will create a curve which is called a hyperbolic function. It is not, as it may appear, parabolic. Definitely not parabolic. And it also can be referred to as a catenary. The simplest form of a function which fits this curve is y equals a half of e to the x plus e to the minus x. And we're going to be studying these kinds of functions in much more detail in the next few videos. So if we start to look at y equals cosh x in a little bit more detail now, the standard definition of cosh x is a half of e to the x plus e to the minus x. And we can start to build up a graph of cosh x if we think about the graph of e to the x, which we've seen many times before, and the graph of e to the minus x. Then if we add these two graphs together and divide by 2, or think of it as taking an average of these two graphs, we will have cosh x. So there is the graph of cosh x. Although it looks slightly parabolic, it is not a parabolic curve. If we look at the values of x, its limits, as x tends to infinity, we can see from the graph that cosh x will also tend to infinity, and as x tends to minus infinity, cosh x will tend to infinity as well. In fact, cosh x is symmetrical in the y-axis. We're now going to look at a little bit more detail on shine x. Just a quick word about pronunciation. Some people call this sinh x or sin hx. I'm going to call it shine x throughout these videos. So the definition of shine x is a half of e to the x minus e to the minus x. Notice the minus sign. And again, we can build a visual by looking at e to the x and minus e to the minus x. And if we add these together and divide by 2, for example, when x is 0, we'll see that it must go through the origin. And in fact, shine x looks like that. As x to infinity, shine x will tend to plus infinity, and as x tends to minus infinity, shine x tends to minus infinity. In fact, it has rotational symmetry at the origin and is an odd function, which we're going to look at now. So they are the graphs of y equals cosh x and y equals shine x, and we're going to look at a couple of important properties. So if we start off with y equals cosh x, and if we look at what happens if we replace x with a minus x. So let's substitute x for minus x. So let's look at cosh of minus x using our standard definition. So that must be e to the minus x plus e to the minus x over 2. And with a little bit of rearranging, we can see that we've got e to the x plus e to the minus x over 2 again, which of course is cosh of x. So cosh of minus x is exactly the same as cosh of x, which means it is an even function and it has symmetry in the y-axis. If we look at y equals shine x and do a similar thing, so let's have a look at the shine of minus x using our standard definition of shine. So that's e to the minus x minus e to the minus x over 2. And if we rearrange this, we will get minus e to the x minus e to the minus x over 2. So I've pulled out the minus as a common factor at the front, which of course is minus shine of x. And we started off with a shine of minus x. So shine of minus x is the negative of shine x, which is the definition of an odd function, which means that shine x is an odd function and has rotational symmetry about the origin. So these are important properties to be aware of. Cosh of minus x is cosh x, so it's an even function, and the sine of minus x is minus sine x, it's an odd function. So they may help you remember which graph is which as well. So what happens if we take sine x and add cosh x? So using our standard definitions, which are going to be very useful throughout these videos, if we take e to the x minus e to the minus x over 2 and add on cosh x, that's e to the x plus e to the minus x over 2, then we can see that if we put all of this over a common denominator of 2, then the minus e to minus x and the e to the minus x will cancel out, and we'll just have 2 e to the x, which is e to the x. So sine x plus cosh x is e to the x. So if I added these two functions together here, so 0 add 1 is there, I'd find another few points, and in fact this would look something like that. Cosh x plus sine x behaves like e to the x. So we're now going to take a look at our third hyperbolic function, tanh of x, and tanh x can be defined as sine x over cosh x, and again we can see similarities with the trigonometric functions, but we are not dealing with angles, so x isn't an angle, but there are similarities to the trig functions. So if we look at cosh x and sine x again, so tanh would be the sine function divided by the cosh function, and would look something like that. So there's the graphic of y equals tanh x, and we can see there's some asymptotic behaviour there, which we're going to look at shortly. There's also a standard way of writing tanh x in terms of exponential functions. So if we go back to our definitions of sine and cosh, so we've got e to the x minus e to the minus x over 2, and we're dividing it by e to the x plus e to the minus x over 2. If we reciprocate this second fraction and turn it into a multiplication, we get e to the x minus e to the minus x over e to the x plus e to the minus x. And if you multiply top and bottom by e to the minus x, you get 1 minus e to the minus 2x over 1 plus e to the minus 2x, which is, if you need it, the standard way of writing tanh x defined in terms of the exponential. And a couple of other important properties of tanh x. If we look at the graph, as x gets bigger and bigger, tanh x is getting closer and closer to 1, and as x tends to minus infinity, tanh x is getting closer to minus 1. So just summing things up now, if we look at the range and the domains of each function, so these are useful things to be aware of to go alongside knowing what the graphs of these functions look like. So if we look at cosh x, the domain or the input of cosh x is x can be any real number, so that's the formal way of writing it. X belongs to the set of real numbers. The range or the output, if you like, is y is at least 1. You can see that on the graph there. If we look at the sine x graph, the input, the domain, is that x again can be any real number, and the range, the output, is y can be any real number. And looking at the tanh graph, the input, the domain, is x is any real number, but the range, the output, is it gets closer to the asymptote at 1 and closer to the asymptote at minus 1. So these are the range and the domains of these three hyperbolic functions, and just to remind you, x is not an angle, it's not a measure of an angle. So in the next session we're going to be solving some simple equations using hyperbolic functions.